Hey everyone, and welcome back to The Explainer. Today, we're launching an investigation into a topic that sits right at the collision point of environmental impact and serious financial risk. We're going to trace the true life cycle of water in hydraulic fracturing, which you probably know better as fracking. And look, we aren't relying on rumors or industry spin here. We are basing our entire journey today directly on the rigorous disclosure standards set by the Sustainability Accounting Standards Board, or SASB, specifically for the oil and gas exploration and production sector. So get ready, because the data we're about to explore reveals a completely hidden world of operational risks. So let's dive right in. Where does the water actually go? It sounds like a super simple question, right? But it actually frames this massive environmental and financial mystery. We already know that extracting oil and gas from shale requires huge, almost unimaginable amounts of water. We're talking enough to fill several Olympic swimming pools just for a single well. But what happens to all that water after it's pumped into the ground? How is it managed? And honestly, more importantly, how do investors and the public actually know if a company is handling it responsibly? The answers to these questions are absolutely critical if we want to understand the long-term viability of these operations. To figure this out, we have to look at the rulebook. Enter the SASB framework, which is now operating under the International Sustainability Standards Board. Our entire investigation today relies on these incredibly stringent accounting metrics. You see, these aren't just vague, feel-good guidelines. They're strict rules designed to bring hidden operational and environmental risks right into the light, allowing investors to actually make informed decisions. It's essentially creating structured transparency where there used to be a whole lot of guesswork. Okay, to make sense of the data, let's map out the physical life cycle of a single drop of water on a fracking site. It's basically a four-step journey. First up, the withdrawal of fresh water from the environment. Second, the injection of that water deep underground. Third is the flowback, which is when that fluid returns to the surface. And finally, the incredibly complex process of discharge and recycling. Try to keep this map in your head, because it really anchors the whole investigative journey we're taking right now.
Part 1, the thirst of fracking, with withdrawing in high-stress regions.
Let's start right at the beginning with the massive withdrawal of water from surface, ground, rain, and municipal sources. This is where the physical footprint of an oil and gas operation first really hits the local environment. So the crucial point here is how the industry accounts for this massive thirst, especially in places where water is already scarce. SASB metric 140A.1 doesn't just ask how much water a company uses. It specifically demands that companies disclose the percentage of water they consume in regions facing high or extremely high baseline water stress, as defined by the World Resources Institute. And guys, extremely high stress means over 80% of the available water is already spoken for. This directly links resource scarcity to operational limits. It shows investors exactly which companies are basically risking their entire operations by relying on water in drought-stricken areas.
Part 2, the chemical conundrum, the mystery of fracking fluids.
All right, once the water is acquired, we shift our focus underground to the injection phase. Now, this is the stage that has historically generated the most public concern. The water gets mixed with chemicals and pumped into the earth at unbelievably high pressures to fracture the rock. And the public's question has always been, do we actually know what's in that fluid? For a long time, companies just claimed trade secrets to avoid listing their chemical formulas. But SASB metric 140A.3 pushes for total transparency. It requires companies to disclose the percentage of their wells where they publicly list every single fracturing fluid chemical used. They want companies to put it all out there, even the proprietary stuff, to aggressively mitigate reputational risk and community pushback.
Part 3, what comes up managing toxic flowback.
You know the old saying, what goes down must come up. And that guides us right into the third phase of the journey, where the injected mixture inevitably returns to the surface. But spoiler alert, it doesn't come back as clean water. It brings up a host of new, really complex hazards, and managing this return is a massive logistical headache. But before we look at how companies handle these hazards, we need to clearly define two distinct types of wastewater. First, we have produced water. This is the naturally occurring, incredibly salty brine obtained directly from the hydrocarbon formation strata. Flowback, on the other hand, is the recovered fracturing fluid returning to the surface, literally the chemical stuff the company just pumped down there. Demystifying the difference here is key to understanding the specific chemical footprint of the site. So, what do they actually do with all of it? Well, SASB metric 148.2 forces companies to break down exactly how they handle this generated volume, and they have to be very precise. Companies must report the percentage of water that's discharged into the environment, the percentage injected back into disposal wells, and the percentage recycled for use in other drilling operations.
It really highlights the ongoing challenge of wastewater logistics and shows us which companies are actually investing in recycling technologies rather than just, burying the problem.
And the exact unit of measure used when this water is discharged, it is brilliantly strict. They aren't just tracking the volume of water. The standard specifically requires tracking the metric tons of hydrocarbons left in the water that ultimately gets discharged. It leaves absolutely zero room to hide traces of oil or gas. It forces a hard, quantitative look at exactly how much residual fuel is slipping out of the treatment process and into local ecosystems. Part 4. The contamination risk, tracking groundwater deterioration. This naturally leads us to the most severe environmental risk of all, the actual deterioration of groundwater and surface water quality around active fracking sites. SASB metric 148.4 is extremely specific about what constitutes a problem, detailing the exact chemical markers that trigger an official deterioration event. It isn't just a vague sense of pollution. If testing finds the presence of thermogenic gas, which is gas formed deep underground from heat and pressure that wasn't there before, or a sudden spike in methane concentrations by more than 5.0 milligrams per liter, that is a major red flag. Or if they find higher concentrations of dangerous BTX compounds, like benzene and toluene, which are highly toxic, volatile chemicals known to cause severe health issues, then a formal deterioration has absolutely occurred. But think about it. How do you prove a water source deteriorated if you don't even know what it looked like before? That's where a rigorous, almost forensic timeline comes into play. Companies must sample water sources within a 1/2-mile radius of the well. They need a pre-drilling baseline before the equipment even touches the ground, then a follow-up 12 to 18 months after completion, and critically, another check 60 to 78 months later. This long-term timeline ensures operators are acting like environmental detectives. They have to track potential leaks years after the initial drill, holding companies accountable long after the heavy equipment has packed up and moved on. Part 5. The bottom line. Double materiality. Okay, so we've followed the physical journey of the water, right from withdrawal all the way to potential contamination. Now we need to connect this physical reality back to the financial reality for these exploration and production entities. This brings us to the concept of double materiality, how the company impacts the environment, and how that environmental impact inevitably swings right back around to hit the company's bottom line. This entire investigation maps directly back to structured disclosure tables. Every phase, every test, every percentage of recycled water is a line item. This reporting totally bridges the gap between an environmental footprint and a balance sheet risk. By demanding this specific data, investors can see exactly which companies are exposed to regulatory fines, community protests, or even sudden operational shutdowns due to water mismanagement. Let's look at how this builds our core argument. On one side of the coin, poor water management leads directly to regulatory fines, debilitating water shortages in high-stress areas, and severe community disruption. On the flip side, strong water management, like investing in recycling efficiency and using non-toxic fluids, well, it doesn't just save the environment. It actually creates vital operational efficiencies and structurally lower operating costs over the long run. It's a win-win. So looking through the lens of these strict accounting metrics, we've really seen the sheer scale and complexity of managing water in this industry. And I think it leaves us with a critical, incredibly provocative question. How long can water-intensive extraction remain profitable in a water-scarce future? It's a massive question that every investor, operator, and community member is going to have to grapple with. Thank you so much for joining me for this explainer, and I'll see you next time.